Throughout this training, or at any time you need support, there are many ways to contact us. You can follow us on all major social media platforms or email us directly via our website, or you can click the Cancel Connect icon shown at the bottom of this slide on our website to book a consultation with one of our experts.
Hypotheses. Grabbing life by the hypotheses. In this section, we'll learn how to build upon the work that we did in the measure phase by formalizing our hypotheses so that we can test and verify the vital root causes of our problem.
Hypotheses can sometimes be tough to explain even to someone who knows about them, let alone someone who doesn't understand statistics. The problem here lies with a lot of terminology and language that statisticians use. Here, we'll explain these concepts in an easy to understand way.
Because we like easy to understand.
Works for us.
We all have beliefs and assumptions. Some are obviously ones like the earth is round, or that the earth revolves around the sun, or the sun rises in the east.
And some are not so obvious or have varying levels of uncertainties. Does exercising really reduce weight? Who's going to win the next election? Which drug works the best? How many hours of sleep do I need? So what if I come to you and say that eating healthy does not affect weight? Some of you will likely challenge me, but there is a logical structure in which my hypothesis can be supported or not. This brings us to the notion of hypothesis statements and hypothesis testing.
How can we quantify our hypothesis and put some structure behind it? We will set up a way to validate our hypothesis using a set of hypothesis statements. In everyday non-statistical use, hypothesis statements are used to explain what you believe is happening. For example, what's causing a problem or variation in a process? A good hypothesis statement should give a clear explanation that would probably be understood by anyone not familiar with that process. When we do a statistical test of hypotheses, these what we think hypotheses must be written into two hypothesis statements, the null and the alternative. The null hypothesis is noted by the H with the subscript O.
The null hypothesis states that there is no statistically significant difference between groups or scenarios. In the example of the effect of a healthy diet on weight, the null hypothesis states that there's no difference between the average weight loss of a healthy diet and an unhealthy diet. And the alternative hypothesis, noted by H sub A, states that a healthy diet does have an impact on weight loss. We must assume that the null hypothesis is true. In other words, that our hypothesis is wrong unless we find evidence to support that the alternative is true.
When using hypotheses to analyze a process, we document the null and alternative hypotheses, both in words and as an equation. The equation for the null hypothesis is that group A equals group B, or weight with a healthy diet equals weight with an unhealthy diet. The alternative hypothesis equation is that weight with a healthy diet is not equal to, in this case it's less than, weight with an unhealthy diet.
Writing the hypothesis this way may seem like a waste of time, but it will save you from lots of confusion in the end. And how do we test these hypotheses? Well, we observe the process in action and we collect data. In our healthy diet example, we would collect weight loss data over a period of time for a sample of people who regularly eat a healthy diet, as well as a sample of people who eat an unhealthy diet. One way to remember the meaning of the null hypothesis is to remember HO, or HO. Oh, ho-hum, there's no difference. There's no difference in weight with healthy eating. And the alternative, HA.
Ha 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 ha.
Aha! There is, stop laughing. Aha, there is a difference. There is a difference in weight with a healthy diet. Just a little thing to help you remember.
So here's a bit of statistical terminology. The focus of hypothesis testing is whether or not to reject the null hypothesis. The null hypothesis is technically never proven true. You either reject it or fail to reject the null hypothesis. Fail to reject does not mean accept the null hypothesis. It just means that the data didn't support it being rejected.
It's similar to a criminal trial. A person is found guilty or not guilty. It's extremely rare for someone to be declared innocent. Now, the statistical question that we're asking with our healthy eating example is, assuming that the null hypothesis is true. In other words, there is no difference in weight with a healthy or unhealthy diet. What's the probability of observing a sample of 5 pounds weight loss or more extreme than 5 pounds? Let's say that we collected our data and we discovered that the average weight loss of the people in the healthy diet group was 5 pounds. Does this prove that a healthy diet does reduce weight? Well, from a cursory look, it kind of looks like it does. But you'll find that such obvious findings are not always the case when you do hypothesis testing. What if the average weight loss for people who eat healthy was just a half a pound? Would you still be so sure that eating healthy reduces weight? So once our hypothesis statements are formalized, we can prepare to test them with data and statistical tests or by observing the process.
It's all summarized here for you in our beautiful one-point lesson for hypothesis statements. Be prepared to demonstrate your new skills in creating hypothesis statements.
In order to test our hypotheses, there are a wide variety of data analysis and statistical tests you may apply. Some charts that we've already introduced and some new ones that we'll introduce in the data analysis section. Often your decision involves determining which test applies based upon what type of data you have, or what sequence of tests you will run as you narrow your search for causes.
When we are testing our hypothesis with process analysis, it means that we first observe the process in action. We go to where the actual work takes place and we observe how the work really happens, like a Gemba walk. After the observation, the team will typically create a detailed map of the process and then begin to document findings and highlights right on the process map.
In the measure phase, the improvement team tracked their initial hypotheses on the informal hypothesis table. This table provided the structure for the team to capture their ideas of potential causes, and then it guided the team to determine how they might test these hypotheses by assessing the suspected impact, the availability of data, and the potential to observe the cause in action by observing the process. Remember, we used this form in the measure phase to plan what data we needed to collect for our root cause analysis. Any informal hypothesis with a yes in the go field should be formalized to prepare for analysis.
Now we are in the analyze phase and ready to formalize our hypotheses and to prepare to test them with data or process analysis. We start by creating our pair of hypothesis statements, the null and the alternative. As with our other templates, each field on a form includes a note to define the input for that field. In your Excel templates file, you will find a blank form, like the one you see in your workbook, as well as a sample completed form, which you will see here on the slide. Now let's talk through the form.
At the top of the form are the foundational pieces of info, which includes the process name, the problem and the goal statements, as well as the total confirmed impact on the problem. As the team confirms root causes, they'll begin to accumulate the impact of these different causes to the problem. Once they've identified enough contributors to meet their goal, they can decide if it's worth it to continue analyzing or if they're ready to move to the improve phase. The next field is the null hypothesis. This states that there is no statistically significant difference between groups or scenarios. We assume that the null hypothesis is true, in other words, that our hypothesis is wrong, unless we find evidence to support that the alternative is true. In our example here, the cycle time to complete a transaction is the same for transactions under $10,000 and over $10,000. Or we could write it in formula form and say cycle time for transactions greater than 10,000 equals cycle time for transactions less than 10,000. Alternative hypotheses state that there is a statistically significant difference between groups or scenarios. So in our example here, the cycle time to complete a transaction is less for transactions under 10,000 than it is for transactions over 10,000.
The next field is the test method. This is where we explain the statistical test or process analysis method that will be used to test the hypothesis. So this field might say process observation, or it might indicate a statistical test such as a chi-square or scatter plot. Next is the test dates. This identifies the expected or actual date for the test. This is a great way to keep track of all the different activities going on within the analyze phase, especially for more complex projects where there are many potential causes. Because all of these analysis and testing of different hypotheses won't happen all at the same time, and as you run these tests, meaning that we are analyzing the suspected root cause, we learn more and may discover new hypotheses. It can be pretty big to manage and it gets a little bit out of hand sometimes. So keeping track on this table will become a key tool for the team.
Once the team has done the data or process analysis, they can complete the next field, which is the test conclusion. This is where the team identifies whether to reject the null, meaning that the root cause hypothesis was supported, or fail to reject the null, meaning that the root cause was not supported. The next field is very important and identifies the estimated contribution to the problem. If the conclusion is failed to reject the null, this field should be 0. In other words, this supposed root cause is a dud. It's got no significant impact on the problem and we have to keep looking.
If the conclusion is reject the null, we should have an idea of what proportion of the problem is a result of this cause. You may start with indicators such as low, medium, high, and then continue your analysis to obtain more details. Some analysis tools, which we'll learn in the next section, will provide specific contribution percentages. Other methods, such as process observation, may provide more general indication of the impact. A pro tip is to keep all estimated impact in a consistent format for all data in this column. Example, if we are studying cycle time, you may be using minutes, or you may decide to use proportion of overall cycle time. That way we can total up the verified contributors and track how close we are to being able to reach our goal.
And here we have our 1-point lesson for the formal hypothesis table.
Woo-hoo!
With that, it's time to take a little pause now, review your notes, and take the chapter quiz on hypotheses.
Good luck. It has been our sincere pleasure being with you through this part of the training, and we thank you for your dedication to creating a better workplace and an environment that you can truly enjoy.